Hello. Thank you for joining. Hope sound is okay now. Okay. So I think we can start today's webinar. Thank you very much for joining. Welcome. Today I will talk about special demands and narrow questions coming from Milton and multi-channel and Swiss type machines. We've summarized frequently asked questions that comes from shop floor and related with CAM programming of different CNC processes. So we have a set of questions that could be joined under one issue. And today I would like to present them. Today we will talk about interesting features of Milton Swiss type multi-channel machines that need some explanation from programming side and need to be discussed from technical side also. I will show a very nice SolidCAM features and facilities that helps to cover that CNC demands. I mean, this webinar will be technical, so I hope you will not be boring too much. In the first part, it will be quite long. I will talk about some programming issues connected with G-code, and then I will switch on the answers that you may find inside SolidCAM on that questions. Okay, I think we can start now. So I will use my presentation. I have tips here to explain. And the first and the biggest item I would like to discuss today is a part transfer. We had a lot of questions about this process, and to show it, I will start from one channel machine because I believe if you do understand how it happens on one channel machine, it will be easier to move to more complex machines. And there are many questions and issues that could be covered under one channel machine, and it will be easier to understand this process on more complex machines. I pointed several items here that I would like to cover and how this process is organized on the machine itself. Okay, I call it important aspects. First of all, before you will start to plan your transfer, you need to understand what actually will happen on machine. This is very important because if we don't have this information, what should be on machine step by step, we will not be able to represent it correctly inside the software, because the software SolidCAM is built that way that it repeats the logics of machine itself. This is why it is easy to use. It completely repeats what you're doing on machine. And how you start to set up your machine, you starting from some predefinitions, you starting it from planning. You should understand how the system will looks before you will run a G-code. This is the same what we need to provide these processes inside the software itself. So let me show you how I would like to see the transfer process and how I suppose it could be covered when we look at it both on the machine and in SolidCAM. First of all, we need to find out what type of transfer we would like to provide. This is how I call it. First point is if this transfer will be with cutoff or without cutoff. I mean, for example, on a picture on the right side, you can see the transfer without cutoff. It's clearly seen because the part is clamped with two spindles and there is no space for cutoff. This is done for big pieces of part, quite heavy, and they are already their shape and length already very close to what it should be at the end, so they don't need a cutoff. They don't need just to be transferred from main spindle to back spindle. That's all quite simple process if you do not know the details of this process. And you may have it with cutoff. That means that we need a tool call and we need a cutting operation inside. So we need some preparation of machine. We're doing cutoff, and then we're moving a back spindle together with a piece of part that was cut off previously. Okay, this is how it works. So transfer with and without cutoff, it differs, and we may create different versions of this process for the software also. Then if we're doing it without cutoff, we need to decide if we need rotation of stock, rotation of spindles during this process or not. This is a very simple process if we don't provide rotation. So that means that our spindles will not be rotated. We will have M5 command, for example, and back spindle just go to the main, clump the part and go back, and main spindle will be unclumped for sure. And we can have this process with rotation. Even if we do not have cutoff, some prefer to provide it with rotation. There are reasons for it. For example, maybe we have a nice surface and we have a rotation back spindle with rotation soft jaws. They were prepared previously, and we needed to make it more to do this process more softer for the machine also. There are some constant cycles with rotation but without cutoff. So it could be, but it needs to be planned in advance. Then the process will differ depending on the bar shape. It could differ. If it's round bar, it is simple and clear. We do not need any preparation, maybe just rotation, or without rotation if we don't have cutoff. And we may have differences in the process sequence if we have a bar with not round shape. It is possible on a mill-turn machine. This is why we love them. We may use not round stock there. It could be for example, square or 6 sides stock, and it's very successfully could be cutted on a machine. There could be special fixtures, for example, for to clump this type of stock. There are fixtures, collets and jaws and so on, depending on a clumping system on machine. But for this type and shape of bar, you need to provide synchronization by angle. It is called phase synchronization. And the back spindle should be synchronized not only with spin, with rotation, if you're doing it with rotation, but also should be synchronized in phase. It's like angle C0 of the main spindle should be the same as C0 of the back spindle. And this process needs not only programming, it needs preparation and settings on machine before this process will be started. For example, there could be a case when your G code is okay, output is okay, but it's not okay on machine because there were no preparation on machine. The C axes or any angular axis that is represented on machine should be prepared. You should find where its reference position. You may change it, by the way, on machine, and where is zero position of angle and how it match with the back spindle, with the main spindle. So it should be synchronized. Okay, and after that, when it's done on machine and when these presettings was founded, then we can represent it in a G code and commands will be okay. The next point when we consider transfer and what we need to pay attention on is a type of programming. There are situations on machine where when we don't have explanation of how this process should be represented, and it's quite not easy task when we don't have any tips from a machine supplier, for example, or codes, G-code examples. In this case, if it's okay, the better scenario is when we have this example and we need to understand GNM codes, and there are only GNM codes inside this example, and we have explanations in the documentation. This is why documentation is vitally needed for some machines to create a post processor and to provide all demands. And in some cases, we have to mix M and G code from ISO with internal CNC cycles that's provided with machine, that provided with the supplier. This situation is possible also, but again, we need to decrypt the CNC cycles, what that letters mean, what that values mean. But today I will show you an example of such a cycle. Its advantage is that it is short. The second advantage is that on a CNC machine, some machines has nice pictures and explanations what's inside, but not all. But for sure, it is the disadvantage that it is not clearly readable when you have it when code is run on a CNC. And we prefer to represent it with GNM codes because it is more flexible structure. You can change it, and you may have less versions and options and less choice. It will be quicker when you're using it inside the post processor. The choice will be quicker than when using CNC cycles. Then one more important question here is the coordinate indication. How you will calculate the coordinates of all devices that will be used during transfer. What devices we will use there? Main spindle, but there is depends on machine. Okay, on this machine, the only coordinate from main spindle that comes to the output is angle position of C-axis. For some machine, the main spindle may also have more axes. Then we have position of a turret. In this case, it's a rotary turret, and my first examples will be related with rotary turret, but for sure, turret type could differ. So it could be spindle with B-axis, it could be some linear turret, and so on. And the third device here that we will consider, it's a backspindle. And in this case, in this particular case, it is the linear position of backspindle. It is extremely important how backspindle approaches to the part and where it is clamped on the part. Okay, and for all these devices, we can use different output of coordinates. And when we're looking code through, we need to understand what that means and what you prefer to use to your constant cycles of transfer. The same for turret position. We may use different turret position. It could be simple safety position, like it is indicated in a part coordinate system. It could be reference position. So that means it's a special command. By the way, the command can differ, and the turret may have several reference positions, and they are written inside CNC. Again, it's a preparation of machine, and we all should know about this preparation, and these values exist on machine. And for sure, the output for cutoff, it should be in a part coordinate system also. Now, for more aspects here, is if we do need a tool change during transfer. Because the simplest transfer could be done without tool change. For example, we need only to move our turret to some safety position, and then we are ready to move back spindle and so on. In some cases, and for most machines, we have not too much space, working space for this sequence. when we have a deal with rotary turrets, they may have quite big holders that take quite huge space here, and there are only a few space for some movements in the working area, and also there could be some parts of machine, and we may have dangerous situations nearby, so we need to be careful. And this is why I included this process here, because some machines need it, and really, and some not. We may have enough space for this and may not, and need visualization to check if everything will be okay during this process. And there could be situation when holders are quite big. We don't have space for a back spindle. For example, part is short. We may also, by the way, apply special fixtures here that will help us to make this dangerous zone longer. I mean, we may have more space here. It could be safe. Because of the fixtures, but we may need to choose, and this is also will be tool change. For one side, it is tool change not for a tool, it is tool change to get more space for the transfer process. And for sure, we will need a tool change if we going to do a cutoff. And it is important to understand when we going to do this tool change. It is recommended to, if you're going to use tool when part is clumped into two spindles, it is recommended to choose and change tool before your back spindle will move to the part. But there could be different scenarios depending on the demands. For example, if we would like to perform some operations on a multi-channel machines, we may have these operations when part is clumped in both spindles, and we don't have choice. We have to change our tool when part is clumped into spindles, and these tool changes could also differ. I mean, the tool change where you have enough of empty space and back spindle in its safety position, we feel good with this space, and we can easily change it normally. Do not think too much about this process. And other situation when spindles are clumped, tiny space, narrow, and we need to provide some special tool change algorithms. So this is also important, could be important, depends on situation. The sixth point here is the calculation of back spindle position. Because how the phase of back spindle position will be calculated and what coordinates will be outputted. It really depends on CNC facilities, but basically I'll show different examples for sure. I will show you. For one channel machine, I would say 90% of these transfers are going in a machine coordinate system, but to apply it, we may need to switch between coordinates. We may need special G codes for this purpose. Otherwise, we may use a separate coordinate system. I think you know that when we have machining, in two spindles, we create a part coordinate system for main spindle, normal, like G54. Then we create a coordinate system for back spindle, which will be used when part will be inside the back spindle and ready for cutting after transfer, okay? And if needed, if really needed, we may create some additional coordinate system to indicate position of the back spindle, and this indication will differs from machine coordinate system. And this indication could comes from, for example, part face, or for example, from clumping point. Some programmers like to clumping point be like 0, and inside the G code it will be outputted like 0, but you need to look in code through to check what lines you had before, and there you will find information about the coordinate system, because they are switching the coordinate system. But this approach needs preparation. You need to move the back spindle before you're going to do a transfer. You need to move a back spindle to a point where you're going to clamp it and to save this position inside CNC, and to set this position as your future zero of clamping part, for example. So this is like preparation in machine, because the first method that used the machine coordinate system, it is easier, especially if you have a proper machine model, and this is what SolidCAM also provides, a machine model, and there we have true indication of coordinates and machine coordinates that you have, and you can just use this model, use our internal functions for this process, and you can save your time and avoid these additional settings on a CNC. But it depends on the processes that are going on a plant. And one more trick that is used here for some machines, also especially for two-channel machines, a position of back spindle is described as a tool. Okay, so we have, for example, an empty tool offset like T99 or something like that, and this is how the position of back spindle is described. And again, the values, the meaning of all this creating of all this system is to have pure values according the face of the part. For example, we do know that when it is, for example, Z10, then we will have 10 millimeters from the face of the back spindle to the face of the part. It's okay. And the clamping position, for example, -15, and this is also will be okay. And this will be easier to read and easier to understand what to expect from machine. So this is important question that we need to know, is how back spindle will be positioned and how coordinates will be calculated. Machine or any additional coordinate system that will be created on machine and will be used inside the G code. Okay. Then we need to pay attention on a special M codes that could be needed. But for example, without these M codes, we will not be able to run a program, even if all coordinate systems and everything is okay. But we can't run the G code because we missed these important M codes. And this is what I will show you also today. It's, for example, when we allow spindle rotates with open jaws. You should understand that this is important when we doing a transfer, because when back spindle is working, we need to unclamp it, rotate, then move to the clamp position, and only after that we can clamp it, and all this is proceeding during rotation. And or some machines needs a special command to provide this process. We need to let it rotate, let rotation with open jaws. This is important, and then we need to turn it on, then turn it off, and the sequence is important. We need to turn it on, then only after that we can open jaws. If we will miss it, we will have an error from CNC. Then M codes for speed and phase synchronization. This is what I already mentioned in the first slide. Then we may have, it is recommended to have to clean the spindles before the process. It is done with air or fluid which going through main spindle, through back spindle, or something somewhere nearby, because if there will be chips, and there will be chips because you did some cutting here, and you're doing clamping, if you will have a chips between your ready nice finished surface and the jaws, definitely you will damage this surface, and it will not be good, and you will have problems with this part. So this command is also recommended to include if machine can do it. Special commands that also could be included, also important, like for example dwell. In some cases we need to wait for 3, 4, 5 seconds while some processes will be completed. For example, this command could be given after we doing some synchronization of speed and phase. For one channel machine, I'm talking only about speed and phase synchronization, because axis synchronization and so on, it is for multi-channel machines, but for one channel machine, what we do have synchronization also, but it is speed and phase synchronization. Speed means that for example, the back spindle can follows the main spindle in terms of speed. It was stopped, for example. We give a command to rotate the main spindle, for example, in 100 revolution per minute. Then we give a command of synchronization, and the back spindle starts to rotate with the same speed without adding any special command to rotate the back spindle. But in this case, it will completely follows main spindle, and if main spindle will stops, back spindle will stops also. This is very nice command, and it is widely used for transfer. And as you understand, if back spindle didn't rotate it before we give this command, it needs some time to achieve the speed and rotation that we mentioned in the G code. And for some machines, they do it automatically. Some CNCs, they will not. I mean, the G code will not run to the next line while they will not achieve this synchronization. But some machines, they need additional dwelling to do that. Okay, so, or there could be some commands that will waiting for process complete. Some other processes should be complete, and there are special commands for that. And for sure, what is used for all type of machines, it's what units will be used for moving of back spindle, for example. We have to, because it's Milton machine, we have to switching between the speed, how it will be calculated in revolution per minute or millimeter per minute. It's like milling mode or turning mode. If we doing a cutoff in this process, we have to switching to different commands, because cutoff is doing like in turning mode, it is clear, and when we're moving a back spindle, we prefer to move it in a milling mode. We're moving it in millimeters per minute, because it is easier to understand how the speed will be represented on machine. Okay, let's go to the next slide, and this is first very simple example that I would like to show you. I took a Fanuc as quite popular system. Okay, so this example will be shown. This is example without cutoff. We have a tool change, but for empty station, and we have transfer with rotation. Okay, so I would say it is most common to have to add a rotation. That means we will synchronize main spindle with back spindle in speed and phase. We have also a special type of back spindle coordinate calculation, and back spindle movement is described in milling mode. So let's run it very quickly. Okay, so at the very beginning, we have, as always, some preparation lines. For example, we turn off fluid to see clearly all this process. As we do not represent a cutoff process, we may turn it off. By the way, for some situations, we have turn it on only for cutoff. For example, for a couple of movements that done for a cutoff, in other piece of this transfer code, it should be off, because we would like to see what's going on machine. Okay, so what do we have here? First of all, it is normal preparation. We turn on milling mode for both spindles. We're choosing the coordinate system of a part, as you can see. We giving a command to unclump a back spindle, and then we have a command to choose another coordinate system. This is switching to a coordinate system of machine. We started from part. It's like, you know, default. We do not use it right now. We will use it lately, but then we're switching to machine coordinate system, and we are moving a turret to the safety position according machine. So this X0 doesn't means our turret will go to the center of the part, because we switched to a coordinate system of machines. So this is machine coordinates, and somewhere upper we describe this safety position. This is one more very nice trick that could be used. It's additional parameter that could be set in advance in the beginning of a program. We may have a list of these parameters. For example, we may have the different safety positions for different tools inside holders. We may have holders, big holders for example, mills, it's driving tools. We may have long boring, drilling tools, or some turning tools, and they may need different reference position. This is position for tool change, but also it could be like retract position. Okay, so then what we're doing as we prepared, we are choosing, selecting a tool, and we're selecting an empty station. We're selecting an empty station because we do not have an offset here. Just T11, and this will help us to have more space between spindles for transfer, to not worry too much about it. And again, we're choosing the third coordinate system. So this is a special command. I would say, in fact, it is not a coordinate system, but this is a special command to move our turret to home position. Okay, so we have a safety position for tool change, and we have home position. But this home position, why it is chosen? Because it is easy to describe it as a zero. Zero is always easy, but also could be dangerous. Okay, so just 5 lines, and 3 different coordinate system is mentioned here. And again, we have one more position to move a turret. And by the way, this could be as these positions, they are like a default, and this position could be shown and could be described as a position as changeable. Okay, so for example, we would like to influence and to output this position, input this position from a software, from SolidCAM, and it's possible. I will show you. And this is described as a machine. So this is machine position. I mean the machine coordinates. So this is position for a turret, Z position in machine coordinates. Okay, then we have air to clean up our spindles before we'll start that process. And we don't have cutoff, but we started to rotate our main spindle. So this is rotation of a main spindle. And as you can see, the speed is very low. And this is the third trick, which is also used as we're doing a speed synchronization. We would like the back spindle follows main spindle. We do not want to enter speed for the back spindle, because we will have to duplicate it and so on. We would like to start, rotate the main spindle, and back spindle should follow it. And this is what's happening on the next line. We have this command synchronization. After this command, back spindle will start to rotate with the same speed as the main. So what's about the trick? We start in it with a low speed rotation, because it will be easier for back spindle to achieve this speed. And after backspindle will achieve it, then we can apply higher speeds, and this what is used for cutoff also. We may start from some lower values, and then after we achieve synchronization, we can run a machine on a rotation that should be rotation speed is achieved as it should be, for example, for cutoff. This rotation still quite low, I think, because first of all, part is has a big diameter, and because we do not need to do a cutoff. We need it only for transfer. What else nice about this command is that this command includes two commands inside. This is also possible. We have in one command, we have both speed synchronization and phase synchronization, angle synchronization of spindles. As we did some milling elements there, it is important because if C-axes of spindles are not synchronized, and for example it's the same C position of main and back may differs. In this case, if you do not synchronize it in phases in angle, when you will do your milling on a back spindle, it will not match with milling on a main spindle. This is what may happen if you will miss phase synchronization. And this is the most interesting moment here. This is a movement of back spindle. As you can see, it is described as a B, like rotary axis, but as we know that this is machine with rotary turret, there is no angular axis besides C-axis. It is described as a B. Also, it could be described as A for some one-channel machines. That could be. And what we can see here, I think this program missed a calling of coordinate system, because as you can see, B-axis clump position is described as 0, but as previously we had a calling of commands of machine coordinate, it's supposed like this is a machine coordinate where B is 0. Definitely it could be like that. In the next example, I will show you how this should be described in machine coordinate system. The value will be like this. It will not be 0. It will not be, some comfortable values where you can see the position of the back spindle from a part coordinate system. It would be some unexpected value in machine coordinate system, quite big with point and some values in the end. It could be. If we apply this one, I can clearly see that it is missed the calling of coordinate system. And this is the question that we may have also. But what is nice here is that we have a dwelling, so we wait till the back spindle will comes to the part, and we can stop and for a second and check what's going on. Also, what we have here is, you remember that we're working in milling mode, so we're using a feed rate like millimeter per minute. In most manual programming, we also adding these commands of how it will be calculated G98. We're adding it here to clearly see how this movement will be proceed. And when we move into clamping position, we're using lower feed for this purpose. This is also very nice algorithm. The only problem here that I can see that calling of the coordinate system calculation is missed. Okay, then we when backspindle achieved our clamping position, we can turn off our blowing of main and back. We're doing a clamping of the backspindle. Again, we have a dwell, so we're waiting clamping will be complete. Then we're doing unclamping of the main spindle, dwell again. And this is also nice short command. B-axis goes to its reference position, and for most machines, I think 99%, reference position for back spindle is away from main spindle as far as possible. So it should be safety, and it's normally used when we're doing transfer for both for one channel, multi-channel machines, and so on. Then we're doing stopping of rotation of spindles. And as we had this under synchronization mode, this one, when we're doing stop, that means both spindles will be stopped. Okay, so we need only one command here. But we need to turn off synchronization, because when we will start any rotation further in the command, they may rotate both if we will not turn it off. So we need to turn off synchronization. And then we're doing some safety retracts, but our turret wasn't implemented in this process, so we may skip it, but it is done for safety, and because this algorithm will be used and could be used for more complex processes. If you may do minimum changes, and you may add some cutoff operation or more complex operations here. This is why they prefer to leave it as it is and to not get rid of these codes that looks unnecessary, but in fact they are necessary, and they are included because it is quite dangerous process, and these zero comments and retracts they are always included. By the way, you can see that at the end we're using some second position tool change position here. You can see this is really nice. This is how you can use G codes together with CNC settings. Okay, I will move to a second example. Again, we do not have cutoff, but here we have a little bit different format for output. What is nice here is backspindle coordinate calculation comes from machine coordinate system. Again, we have all the previous information. We have a tool change to empty station. We do not have cutoff, and we have a pulling part out of main spindle. This is one more trick that is also commonly used when you, as I said, all this setting, I mean a rotary turret together with big holders, it takes place. And if you have quite a small part, you need to clamp it very close to the main spindle. You do not have enough of space to do a cutoff. In this case, we may use a back spindle to pull part out from the main spindle. And this process is also could be included to SolidCAM output. It could be. We need just a description how it's done in a G code, and we can repeat it inside a project. Okay, so what do we have here? Again, some preparation. By the way, for this machine, we have other type of home position output of turrets. Here we have, this is what I like. This is G30.1, 0.2, 0.3. This is what CNC let us to add. In a previous example, we added through parameters. In this example, as we have enough of cells inside the CNC, we can add it this way, okay, inside CNC, and we need only the output inside of G code. Then we need to be sure that B axis is in its home position as far from main spindle as possible. Then we have a safety position for tool change, and this safety position comes from coordinate system, because previously we mentioned it as a G54 well-known command, I think. Then we're doing tool change, then we turning on the turning mode, but lately we will switch it to a milling mode on machine, and this mode influence on if we can use C-axis or not. Because we may do some milling when part is clumped into spindles also, and for this purpose we will need we may need C-axis milling mode turn on machine. But here, as we going to do some we're doing it with rotation, we will turn on a turning mode here. Okay, then we're doing synchronization of rotation here. A special command. As you can see, it is not M3, it's M203. This is how it happens. And with this command here, they will rotate in the same time. Both spindles will start to rotate, and this output differs from the previous one, where we started to rotate main spindle, then we give a M command for rotation of back spindle, and only after that we got a result. This result comes faster. Then we moving our turret to safety position. We do remember that our turret is in x home position. So Z0 means it movements only in Z direction. X direction is still okay. It's should be quite far from a working area that we have on a stock, and this is empty station also. So this is the movement. Again, why we need these movements? Only because this algorithm will be used for some further more complex procedures. And this is what also I would like to show with these examples, that the main sequence remaining the same. It is the same, but some lines and some variables could be changed, and this is what we also will represent inside SolidCAM. The same sequence, but different versions of output, and not too much parameters will differs. Okay, and after that we are ready to move our back spindle, and here you can see the true machine coordinates. So this is how movement of back spindle will looks like. This is machine coordinates completely. This is how it is outputted normally, and as you can see, it is safety position, so it moves on G0, it moves close to the part face, but in the empty safety area. Then we have a special command to let back spindle open jaws during rotation. Then we're doing opening of jaws. Some prefer to do the separation before back spindle comes to a part. In this case, we move our back spindle towards part. It's quite close to a part, and after that we open jaws. And this is the also normal line. We will see this line later also for 2-channel machines, for example. This is how it happened. We would like to do this movement on some controlled speed. Under speed, I mean F command here. This speed should be controlled. This is why we're using G1. Then we mention what units will be used. It will be millimeter per minute, not millimeter per revolution. Then we're using the position, clumping position. So this is clumping position. As you can see, the difference is not too much. Okay, so it's like only 10 millimeters, and it goes towards main spindle on this distance. That means that part is quite not so long. Okay, we do not have enough space for for clumping. I'm sorry. Okay, and then after that we have this clumping command, and then we clump to open jaws on a main spindle and let part to be pulled out. We need to do a pulling out of a part. Then we pulling part out with a back spindle, so it is clamped in the back spindle, and we move it out of a main spindle to some distance, again in the okay. I hope. Anyway, we have a recording. Okay, and so we're pulling part out of a main spindle with this movement, and then we're doing some procedures to Clump, a main spindle, and then we can continue with other processes. We can cut off part, or we may, like in this example, a Backspindle just opening and moves to its home position, and we continue our operations on a main spindle. We may avoid the part to be too far from the main spindle. It's helps us with rigidity. Okay, and now finally we have an example with cutoff. What will differs? First of all, we need to add one more lines which describes a rotation of spindles. So we need to mention, we need to insert a piece of code that shows an actual operation. If you saw SolidCAM tree, you may see there are different types of operations. Preparation on machine, we call it MCO cycles or machine control operations. I will show it later. And we have the actual operations, cutting operations when we're using cutting tools, and this piece should come from that operation, because all this preparation will be basically the same as in the previous example. We are moving the back spindle to clamp position, clamp it, and then we are adding some speed. We had the lower speed. When we trying to do a cutoff, we need to remain some certain speed for this process to remain feeds and speeds, turning modes from, for example, tool supplier. This is important. So we adding this command here. The question is if we need to use a constant cutting speed or G97 command, because our diameter is coming to 0. It depends. And this could be a variable also in the output, what you will program inside the cutoff process, because this also options inside a cutoff dialog box inside the SolidCAM. After that, we doing our cutoff. As you can see, we have X movement here, and one more thing here is that we need to switch to a millimeter per revolution. We're doing our turning operations in a turning mode when we're using feed units as millimeter per revolution. Previously, we had it as a millimeter per minute. Okay, so this also very important, one small command, but it may change a lot. So this is how I think it's absolutely readable how tool moves to its cutoff position. Then we're doing a retract of a tool. It is also good to do this retract with G1, because G0 may leave some marks on the face. And also, this is what I also mentioned. Fluids and cooling, it's turning on only for this cutoff movement, because we would like to see clearly how the previous process is completed. Okay, and then we have a retract of our turret only in X direction, because it is dangerous to retract it in both directions, in X and Z. It will be dangerous because in Z we have a back spindle. And after that, we're stopping synchronization with this command, rotation of main and back wheel stops, and then we moving part together with back spindle to its home position. And after that, we're ready to continue with operations on a back spindle. Oops, sorry. And the final example for one channel machine is transfer with CNC cycle. So this is the real example that we implemented on one of machines, but before we've got an explanation of what this cycle consists of, what these letters means, values means, and so on. As you can see, we can't have only this cycle. Basically, we need preparation. Again, we need some preparation. We need normal GM codes before and after. And only after that we can apply this type of cycle. Its advantage is that it is shorter. Yes, for this machine, for example, customer couldn't find out what's inside the cycle. There were no interface for that. Some CNC, they have it. So we need to know what's inside, what all these values means, and they may have unexpected values. For example, this value of clumping, again, it is in machine coordinate system. Okay, it's clumping value, but other values, they describe the distance safety approach from this value. This value, you know, like a base and 0, and other values, they describe the distance from this value to safety position and to what happens here inside. There is no cutoff here. It's only a transfer, the simplest code. If we adding a cutoff here, it would be more complex. Okay, so as we found how this process happens on one channel machine, we can move to the two channel machine, and I would say it will be easier. If you do understand how it happens on a one channel machine, all these rules, most of these rules are transferred to two channel machine, to Swiss type machine. They will be a little bit complex on that machines, but main idea and all these you know, special commands to switching between modes and so on, they will be the same. Commands itself will differ, format will differ, but the sequence and the logics will be the same. What highlights we have for two channel machine? First of all, for sure, we have two G-code files. So we have to separate that code on two channels, and we need two files. And when we're asking for this information, we're asking for two files to find out how this process is described there for machine. Then we have what is new for us in comparison with previous machine, is that we have weight marks. This is important, weight marks, and they differs from machine to machine, and they could be really unexpected output for weight marks. Some codes, they are not called and they're not considered as weight marks, but they're working as weight marks. Backspindle, that movement is controlled under second channel, and this makes situation easier when we move it and when we're trying to calculate coordinates for backspindle, because this axis becomes control of this axis is more flexible in this case. It is not maybe convenient to have it in a second G code, could be, but it is quite easy to manage it and control it under second channel. Backspindle coordinate calculation still may differ. You may use different approaches for that, and also there could be special functions to control second channel from the first channel and vice versa. Okay, let's move further here. So this is example that I would like to consider. Also, this is example for two-channel machine, and this is what we call a weight mark. So this is a special commands. We can say it is G or M commands, just separate special additional commands to divide the G code and to weight. Okay, we call it weight marks. That means one channel will wait, something will happen on other channel. Okay, this output is for Mitsubishi. So this is again, we have preparation. We're starting from the first channel here because we're going to transfer part from main spindle to back spindle. We're starting from first channel and we're doing the same as we did before. We are having some basic start rotation of main spindle. We're switching to coordinate system. We have less switches between coordinate systems here. Some machines has internal variant cycles to do it safety. But again, we have a retract of a turret. I think I suppose this machine has some other type of turret. By the way, it's not rotary, but I don't remember, and I think it's not too important right now. Just we always remember that we have retracts, and we remember that these retracts can differs, may have different points, and differs depends on G code that used there. Then we have a tool which will be used for cutoff. For two-channel machines, we're using it for transfer. Is always not always okay. Frequently, it's with cutoff. Then we have preparation of position. It's z-axis position, and this will be position for cutoff itself. Here we have a cutoff, and we do not have any z movements here because again we have not too much space between spindles when they both clumped, and we prefer to prepare our z movements in advance or before back spindle will be clamped on a stock, if it's possible. This is a special command for synchronization of speeds and phase. After this command, the back spindle will start to rotate with this speed, which was mentioned before. Then we have this waiting command, and we're switching to a second channel. This piece will be on machine, and the first channel will do nothing during these procedures. Here we have some confirmation commands, and this is what is interesting here is that this is how we're calling a back spindle. For two-channel machines, it is quite common to indicate position of back spindle with a coordinate system which is set through tools offset. For sure, to find this position and to have these nice values, so this is 10 millimeters before part phase, this is 3.5 millimeters of clamping position, our future clamping position, and this is calculated from this coordinate system here. How it's possible? Because there was some presettings on machine before all this program will be run on machine. We have our part ready for transfer. We stop everything. In manual mode, we take a back spindle, move it towards the part, touch a face of the part, and this is how we find out the offset for the back spindle. The only trick which is used here is that this offset is setting to a tool number. Okay, and this tool number by default used only for back spindle. So this is how face of the back spindle knows where is part 0, because different fixtures can be used there. I mean jaws, or maybe it's a collet, with long noise. I mean it's not constant, and the position of part face is also not constant. They could differ. But when you're doing a series of parts, a lot of parts, not one, it makes sense to create such a coordinate system here. And this is what also we need to represent inside SolidCAM. We need to represent the calculation of position of back spindle both from machine and from other type of output. And this is what we can do. Okay, so now we clumped, we moved back spindle, clamped it on a part, and we're ready for cutoff. And as we're ready, we adding a speed of rotation as it should be for cutoff. Then we're doing a cutoff itself, no Z movement. So this is safety position, this is cutoff position, this is retracting of a tool, and safety retract of a tool again to some safety far position. This is what this happens in a part coordinate system. Then we're clumping, then we're moving back to a second channel and retracting backspindle together with part to its home position. By the way, here on this machine, backspindle has two linear axes. It has Z, as we saw on one channel machine, and also we have X position. This is also possible. And because of this, when we're doing preparation, we did it with X position also. And you can see that it was done under G54, because if we will output it in machine coordinate, that here we will have some unexpected value like minus 434, something like that, that it is not easy to understand where it is. But with these values, it makes program easier to understand. But these values will be according a part coordinate system and needs preparation. This command is to turn off synchronization of rotation and phase, and this is retract of a turret. And then we turn off rotation itself. So as you can see, this sequence is basically it is the same as for one channel machine. The difference is that it divided into channels. We have weight marks, and we have this trick with coordinate system of backspindle. That's all. Other things are retract, safety positions, and so on. They differs in formatting, but sequence basically is the same. And please remember this picture, because I divided into blocks with weight marks, and this is what we have in a SolidCAM. This is what we have from a software, and this is why we always tell and we talk about SolidCAM follows sequence of on machine. This is why it is easy to understand. It don't need too much time to study how to do it inside SolidCAM, because logics is the same. We have very nice, excellent visualization of the process. I will show you all these features lately. First, I'm sorry it is too long. I know it's too long, but if we do understand how this process proceeds on machine, then and it is very close from one channel to two channel movement between them. It's a small step between them. If you understand the logics, if you understand what machine needs, if you understand what pre-settings should be done on machine, you can easily represent it inside SolidCAM. And we processor side, and this is how our channel synchronization table looks like. And all these blocks, all these pieces is the same as you have here. It's absolutely, I would say, naturally, no special transition needed. These black lines are your weight marks. This is how you can divide it. Okay, and what's the last point here on the transfer is what's the difference with Swiss type machine? The difference, the first one is a special command for this synchronization, because for what's the actual difference between two-channel, multi-channel machine, Milton, and Swiss type? The main, as maybe you know, is how we moving how Z coordinate is represented. We are moving our bar in Z direction, and this piece here on a slide from the right side, this is the device which moves our bar, and this device is guide bush. It's not moving, and we can see this movement. It comes under cover. Okay, it gives us advantages because tool is always very close to the stock. We don't have this we have rigid cutting. Yes, we have advantages, but also we have disadvantages from this process. And disadvantages should be also covered, and we need to care about these disadvantages. And these disadvantages, they give us special commands that should be covered when we're talking about transfer and other processes. We need the Z-axis synchronization because the main movement here is movement of a bar. And when we clumping part with a backspindle, we have to synchronize Z-axis because our main Z-axis comes from this device here. It moves in Z direction, and when part is clumped to spindles, and we would like to do, we can do a lot of operations here, by the way. We do not need to pull part out with the backspindle. It will move. It will naturally move with Z-axis, but we need to synchronize. Synchronization means that backspindle axis will move after Z1 from main spindle. We need to input just one command in one channel, and it will be accordingly done with the second spindle without any additional commands. And this is how, for example, we may represent toning, very rigid toning with two spindle and one tool. Part will move, and tool will be positioned only in x-axis, for example, for toning operations. This is very nice and very useful. We need this command, and this command is recommended to use when you're doing a cut-off process also. It is recommended to be included. And this is what is by default included to our post-processors also. And the other differs from the previous one, special for Swiss type machines, and also could be missed, that tool stays in X lowest position after you did a cutoff, like you can see on a picture. So you doing a cutoff, you have, for example, X minus 0.2, and your tool stays there. It waits for bar change cycle will be proceed on the first channel. It stays here, and in this moment, backspindle with part can come and do some cutting on other turrets and so on, but tool should stay in X lowest position. This is like a requirement, and this is also what could be found in the documentation. The next point here is that we need to calculate and prepare the one bar stroke, because we may have very long bars here, as you know, for Swiss machine. This is why we love Swiss machines. We can 24 hours we can run it, we can make a lot of parts here, and we do not need a lot of manual changes if bars are okay, if our bar feeder is working and program is okay. We can do it, and it's very efficient, but we need to recalculate the position of these strokes, and for this purpose we're using a special approach, special variables, depends on machine, or special commands, special cycles, and this also included to SolidCAM. This is also what we have. I will show it. Okay, then cutoff position and offset point tool effects on Z1 position and output for sure. This is also, we have a preposition, we have a cutoff position, and we may move bar during a cutoff. For example, you would like to make a chamfer there, it is okay, it could be done, but we need to apply a special cycles. We need to apply a special maybe access patterns, and this is 0.5 access patterns. Some machine needs them. I'm talking about mostly about Citizen. In Citizen, it is represented with a separate codes. other machines like Tsugami or Star, they have it like in hidden mode. It is not shown as access patterns, but there are special M codes that describes this switching between different axes, because the same tool and turrets may works in different modes, could be controlled from different channels. This is what access patterns done. This is yes, access pattern is could be quite complex to understand while you didn't saw it on machine. Also, it depends on machine construction. If you do not have too many turrets there, it could be easy, but for some machines it could be quite complex process. And also it could be additional weight marks and synchronization codes inside. I would like to show it on an example. Again, I will represent this G code as a divided, separated structure, okay? Because I like to show this structure every time I'm showing it. I like to show it because it is so close and easy to make a transition to our synchronization table. It is the same. It is absolutely the same. This is on the green. I marked what is called access patterns, and these access patterns for Citizen, for example, it has a lot of hidden functions. Okay, you may have some machine movements and preparations inside this G code. You will not input it manually or from a CAM system to a G code, but a machine will move under this one line. It doing some preparation. For example, it will preposition a backspindle to X0 position, for example. I mean X position to do a transfer. So backspindle will be moved right opposite to main spindle, and it will be prepared. And for sure, it will also prepare machine access. Machine will know that under these access patterns, access pattern, it is ready to do a part transfer or some machining when part is clumped into spindles, but they could be, it depends on what we're going to do. Basically, this is used for part transfer. And again, as it is Mitsubishi, we for multi-channel machine, we saw Mitsubishi also, and we can see that commands are the same and the preparation are the same. We're choosing tool, we're choosing a rotation, we're choosing some preposition point, and this is what also added from the previous multi-channel two-channel machine. It's a weight code, the same, because it's Mitsubishi, format is the same. This is why I've added this example also. That means we will wait for channels will wait for each other, so they will run this code till this L code, and also this L code will be used inside during the peak of process. Okay, so for example, this part will not start while this part will not be proceeded, will not be done. Okay, it looks like they go in parallel. So this part, I think you guessed that this part is the movement of backspindle to clump position. Again, we're using these codes. I think it is clear what that means, because it is absolutely the same. As you can see, again, we choosing calculating a position of backspindle through the tool offset here again, but the tool number is differs. But again, we're moving backspindle and we're clumping it on a part, but we're doing it before this waiting mark. After this waiting mark, we can do a cutoff itself. Okay, this is what we're doing. This is the cutoff, and it is recommended to have the same points for z-axis, for example, because this is done under z-axis synchronization, and if you have some movements in z-axis, all your system together with backspindle will be moved. But some cuttings, they need these movements, so it's okay. Okay, so this is what we're doing. We're doing a cutoff. As you can see, cutoff tool is in its lower position, and we can see how this how tool will retract. This is what I told you earlier. As if you will check this code closely, you will not see any movements in X direction, safety, or whatever tool stays in its lowest position and it changes it or with the beginning of the program when the new let's say part will be loaded. Let's call it like this, but it's not loaded, it's just moving of a bar. Okay, so we just moved our cutoff tool to its lowest position. Then we're doing retract after cutoff, and this is why we talking about hidden codes. Here we can see that comment that the backspindle should be retracted, but we can see G codes for this purpose because it comes under this weight mark. This weight mark has this movement. Automatically it will move to retract position out of a main spindle. And this is a bar exchange program piece, how machine prepares to a new part. Okay, so this is how it looks on a Swiss type machine. I think if you understand the process from the beginning, from the one channel machine, it is easier to understand it. It's even the code is even easier than for the one channel machine, I believe. Because for this machine, most of the job is done with machine itself, but you need to care about coordinates for sure. And if we will analyze this process for different parts, for example, we will find that there are not two variables to change. Most of the code will be the same. You need just several variables to change. And I think I would like, yes, I would like to show you how it could be done on machine. I have a small example here, and this is example with transfer, and this is how we are doing it on inside the project itself. Again, I think it is clear that also I will repeat it again. We need to understand that the logics of machine will be this will have the logics inside SolidCAM will be the same as you have on machine. How you starting your machine preparation? I think for two-channel machine, for example, you starting it from setting on tools. Oops. Tools and holders. Okay, this is how you're starting. You put all tools where it should be. You find the offsets. You may find offsets for the backspindle if you would like to represent it as a tool. You're preparing your bar and so on. The next step for Swiss type machine, for example, and for other machines is what we call under setup window. This is what we have, and our loved feature machine preview. It helps a lot if you have a machine model. Here is a preparation. So now we do not have any bar, any material here. All material and bar is behind the guide bush. Okay, and we have this device. Let me show it to you, which moves, for sure it should move like this. It moves our bar, okay, towards the working area, and this device is clamping and moving and preparing bar. We may have very long bar here. It depends on bar feeder, 5 meters, for example. It could be 3 meters. And this device is responsible for that movement and for this reclamping and so on. And we need to prepare all this system. For Swiss type machine, we need to calculate the length of the bar which will be needed for that particular part. And from this calculation, we're starting to add information to this table. For example, like this, we measure it, and we know that we need about 70 millimeters with all allowance, offsets, and tool positions. Also, we need to define coordinate systems because, as you saw, and it is also taken from one channel machine, we have a coordinate system on a face of the part for first channel, and we have a coordinate system. Let me do like this. we have a coordinate system to machine part on a backspindle. It differs different coordinate system. It could be G55 or something like that. It differs, or it could be G54, but in the second channel because we have two-channel machine. But it differs, and this is what you also need to do inside SolidCAM. You need to set your coordinate system where it should be, very naturally, and you also, with this dialog box, you're choosing in what spindle you're starting your machining. For sure, for Swiss machines, it's also always starts from main spindle. But if you have two-channel machine, it could be situation where you need to start it from the back spindle. It could be, why not? And you have this facility here. And what is also important here, as you saw, is here we can show, and it is recommended to add information where part will be clumped. Okay, this is also what is planned. You plan in this process before you start writing your code. You need to understand where part will be clumped, and this information also added here. You add it here, and it will be outputted automatically, and all other processes will be automated. Okay, so this is preparation. Preparation on machine is the same you may have inside SolidCAM. Quite easy. Then we're doing our normal cutting, and we are ready to do some transfer. And for this purpose, we have our special MCO operation or MCO cycles. I think I can go back to presentation and to say a couple of words about cycles. And okay, machine control operation, I will explain what's the difference. Okay, machine control operations was designed to operate machine outside cutting process. So as I said, we may have cutting process itself, milling, cut-off, facing, turning, and we may need, as we saw with transfer and so on, we may need some movements of machine devices out of cutting itself. So the movement of back spindle, switching to different coordinate system, preparation of a bar, and so on, changing tools, moving turret with tool without cutting to some positions. This is why we implement machine control operations. You can see I just described what we may have with these operations, but list is really long. We can add custom functions and so on. And we may have cycles, machine control cycles. They designed to quickly reproduce repeated constant processes on machine. This is what I showed you. Transfer could be considered as a repeated constant process with different variables, or as several processes depending on machine and depending on demands. And you do not need to add all these long sequence, open, close, for example, error. You may forget something. It's so easy to forget. But if it will stays in some cycle, if it stays inside program itself, it will be constant, and you will see only changeable variables. Like, for example, you can see on the slide here, like, for example, position for z-axis. This is the cycle to position a bar, for example, on a Swiss machine. If we need to move a bar out of cutting process, we need to hide it. It should move to call it, so it will be like a safety area here and so on. And we need to add information what speed should be applied there and so on. It could be shown as a parameters. It's a predefined set of customized repeated machine processes. What this is MCO cycles. It is done from MCO operation, and we can return MCO operation to a cycle, and you will use only variables that you need. You do not need all that long sequence. MCO cycle interface shows only changeable parameters all repeated commands stays on a background, MCO cycles stored inside VMID file. This is important if you would like to know if your post-processor has any cycles. Just open this window with MCO operation and check it. I will finalize with this slide and will show how it's working inside SolidCAM. MCO and cycles output comes from post-processor. So MCO comes from two places. Basically, its interface and content comes from machine ID file, VMID file, but the output of this content and difference in the output comes from post-processor. And it is powerful programming feature. Okay, let me switch to a SolidCAM. Sorry. Okay. So how to find out if your post-processor has a cycles inside? You just go to machine control operation, open it, and you can see if some cycles are added here. Okay, just click here under technology. If it's under general, you may add some comments, but the output will depend if there is some content inside post-processors. Okay, we may limit this content to not have problems with output, because it could be some unexpected. If you miss something important here, we saw that this process could be quite complex. But when we're adding a cycle, it is if we have a G code, if we have an input about what variables should be added, it's quite easy to add and quite easy to provide together with post-processor. You just use cycle that you need. For example, for these processes, okay, this is a cycle first part of our transfer. We're choosing our cutoff tool and doing some reposition here. Okay, always unexpected when doing it online. I'm sorry for that, but I think it is clear. So how this process could be represented with parameters comes from this cycle. All you should do is just choose this cycle. Okay, now it's better. Choose this cycle and you can see it clearly, and you can change these parameters here, and you can change this together with machine preview as I showed you for a setup. I don't want to choose it right now because I feel that it can have some problems during a webinar because it's online and facilities are limited, but we can. Okay, I will try to check it from here. I hope it will work and will not give me some errors here. Okay, so this is what we can have. We can check how machine looks like before this process. We can check, for example, what tool was used before, where is the part position, where is the spindle's position, and so on. And we may change this together with parameters. So this is quite nice features, and it's based on the sequence that provided with a customer. With variables, we just add variables that should be changed here. And we have the sequence, so this is like preparation cycles. For example, this is axis synchronization, this is cutoff itself. It's a normal operation of cutoff, then return of synchronization of axis of spindle. We're doing retract of backspindle, and this is the special separate piece to provide end of program and bar change. And when it is ready, you did, for example, a cutting on a backspindle. You need to apply a part eject to make this process parallel. When it is done, what you're doing, you go to channel synchronization and apply a synchronization to have it in two channels, whatever you like, what operations should be parallel, what should not, and also you can apply, if necessary, if machine needed, you can apply different access patterns here. Okay, so this is how it's done. If you know how machine doing it, the process transition to SolidCAM very easy, and it is completely the same as on machine. But you have the representation of machine. You have it's like electronic virtual model of machine. If you're setting up all your tools as it should be, bar as it should be, and so on, you may represent all the process before you will move to machine. Okay, I would like to back to presentation, and we'll continue, I think. Okay, the last point I would like to mention, which helps also to set up a machine and to represent all this complex stuff related with mill-turn machines, is a toolkit. And I know that we have a lot of webinars and showing videos also on YouTube, which were not included to webinar, but you can easily find this information. For example, how to add a new tool, how to use STL, and so on. It is also available on YouTube and under what's new, by the way. Everything is described there. There is a set from short videos, step by step, how to use this interface. And I would say these machines, they inspired us to develop a toolkit, because we had a lot of demands from the customers who has mill-turn Swiss type machines, because there are a lot of complex holders. Even, by the way, these holders are used for one channel machine with two spindles and simple rotary turret. This machine is considered as simple, but you may find some interesting things there. And these holders, they're important because you have more facilities. You may have more different cutting processes on machine with these holders. And it will be good to have it. It will be good to program it. And we have this possibility inside SolidCAM. For example, this is a drive holder for milling, and you can manually change an angle. You have a simple rotary turret, but you can do some angle operations with this type of holder, and it will be good to have this output. It will be good to have a representation of this holder to calculate if there are enough of space and so on, and we can do it. We can do it together with toolkit. In our new versions, we can apply different offsets for tools. One tool may have several cutting points, for example. All this is available inside toolkit. Also, we may provide a custom or complex cutting tools inside. This is one of the requirement that was previously, especially for Swiss type machines, because there are a lot of small tools and small cuttings. And also we support for sure absolutely custom shapes for turning tools. And I think this information already was shown previously, but I would like to mention it because this is one of the reasons why toolkit was implemented. I would like to move to more complex things that may be not covered before. I'm sorry again for this long webinar and for this complexity, maybe, but customers who has this machine, they will know what I'm showing now. Some machines, I'm talking about Swiss type machines, they're starting to configure it. They are starting to set it up, not from the setting of cutting tools. They are starting to set it up from adding information about what holders will be used for a current machine, for a current setup. And this is what that picture on the left side is shown. If you also saw our previous webinars about Swiss type machines, we talk about they are like Lego construction. You can use really different holders and you may have more and more tools inside. and machine should know in advance what set of holders will be used. And for this purpose, this is a special menu inside CNC is used. As you can see on the left side, it's a tool numbers, and on this column is described the name of the holder. So name of a holder is inputted to a CNC. I would say it's not really inputted, it is already inside as an option, and customer should use what exactly should be applied for this setup. And how machine also know this, it would like to have additional G code with a set of parameters. As you can see, it's just the numbers. There is no mention of, for example, holder name. Yes, it's just a set of parameters. Each parameter is related with a certain cell here. And depending, for example, this T11, as you can see, it may have 3 options inside. Okay. And under this cell, there is a related parameter here, and this parameter may have 3 different values depending on what will be set there. And customers expected that this information also will comes from toolkit. It comes from the G code that we outputted together from SolidCAM. Okay, and this is also possible. This is why we implemented toolkit. I would like to show more complex situation. As you can see here, we have tool number 10. To this tool, we implement this holder with 3 positions, and to each of these, not each, I think from 1 or 2 positions could be added 1 more holder here. Okay, so we had one position. From this 1 position, we've got 3 positions, and from one of that 3 positions, we have 4 positions more. So this is how Swiss machine works, and all this stuff is described with this additional information. And for sure, we have to represent this information, and we may have this representation together with toolkit library. I hope it will be shown. Okay, so for example, this is what we provide, what we can create together with customer when we have stale models. We creating a library. This is also what recommended for mill-turn machine, especially for Swiss type machine, especially if you have this situation with holders naming and so on. And this is how they are looking like. Let me show it like this. Okay, for example, this is what I can choose. I can see holder itself. It has a special name here, and I can just drag and drop it. It could be positioned not to all stations here, but to some station it could be there. It is described inside the documentation. I can just, for example, drag and drop it to a certain position, and this is what I may have in the output. Also, I may have more complex situation, which I had here. For example, I have T11. Let me show like this. Okay, so this is how structure may looks like. So this is T10. Okay, so this is T10. To that position, I input this B-axis. Okay, this is manual B-axis. To that B-axis, I can. It has three positions inside. To the upper positions, I implemented this type of holder. Let me show it. Okay, it's this type of holder. Okay, and to the lowest, I implemented this type of holder, and I can put 3 more tools there. So this is why we have toolkit, because here, for example, I can choose what tool position what joint will be used here. For example, here I will have T11, T12, this is it, and T13. And under T13, I may also use different joints. As you can see, there are 3 joints. For example, will move it to this one, or to this one. I can move it. This is how I can do it with the toolkit. what is recommended for this case? Again, we just following the machine strategy. Machine described it inside with tool holder name, and we're doing the same. We repeated these holder names. We have this library. Yes, we need this library. We need to create it. We need to add information about joints, because joint is the place where we can, which is described under STL model of the holder, and this place is to fix, to position a tool. And joint name, for sure, you should understand that calling of this tool could be a challenge, because depending on machine, in fact, it is T10, but we can't call it as T10. We have to call it with some other way, which includes all this system inside. And this structure helps us to output the right type of tool calling. This is what I'm trying to explain under this example. So this is information for machine, how this setup will be looks like. After machine finalize this setup and it understands this setup, it knows how tool will be called, because if there is no all this, T10 is just normal radial tool. When we have all this information here, we don't have T10, we have T11, T13, R1, R2. There are arguments also for calling, and machine knows what tool is meant, radial, axial, if it can use B-axis. In this case, B-axis is manual, but there are machines with programmed B-axis. Yes. So I would like to, finally, we're ready to finish. And here I would like to mention several important things about toolkit tips. This is how I call it. For such machines as I showed you, and even for one channel machine, it is really recommended to create toolkit library. It is recommended to take models of holders, to add joints. To add joints there and to describe them. It will be much easier for programming. It will be much easier to check machine preview, to check simulation, and to understand if you have enough of space. And also some machines calling tools based on the holder type. It could be, it happens. Okay, so it's very nice to have this information, and you may have it inside toolkit library. You can move it from PC to PC. You can share it. So it is what will be stored and could be used. Also, it is good to describe holder name and holder join and to not change this name. Okay, it is nice to have the output from post processor based on holder and joint name if needed. Some machine doesn't need it. There are simpler machine that doesn't need it. We did it before. For one channel machine, it is for more complex machine that related the holders on that machine may change output there. Okay, and also it is good to store STL files. There could be situation when you move your library from machine to machine and some representation of holders will be missed in the process. So it is good to store all this information inside libraries, and if you're moving from machine to machine, to copy all this information. And it is also good to discuss post-processor rules that could be connected with holders if needed for machine. To discuss it and to know it, for example, one of the rules for that machine is not to change holder name, because if holder name will differs, we can't output necessary information to a G-code. Okay, thank you for your attention. Thank you for being with me today. Sorry for this long webinar. We have a lot of questions, a lot of technical things to discuss, and it could be more webinars about because I didn't tell you about special milling modes for mill-tone machines. But I decided to focus on the part transfer because I had a lot of questions about these items, and it could be that it's more clear now, and but maybe you will need more examples about this item. Okay, hope you enjoyed. Thank you very much for your patience and attention. See you next time on the future webinars. Please visit our YouTube. There are a lot of, and forum also, a lot of interesting information there that you can miss if you will not go there. Thank you very much.